All right, this is going to be the final assignment for the aerospace or aerodynamics class. This is going to be regarding the XFLR5 assignment. I have all my data complete already. I'm just going to quickly show you my report ahead of time. All the data points look good. There's been no issues with convergence. Everything looked okay. So I still have to finish the report. But anyways, let me get into the tutorial on how I did everything. So once you have XFLR5 downloaded, you can just open it up. Let me exit out of this, go to here, XFLR5. All right, so first we're going to start off with the basic Clark-Y airfoil with no different aspect ratios. In order to do that, you want to go to the UIUC website, download a airfoil of your choice. Mine was Clark-Y. Make sure your leading edge and trailing edge coordinates are in the correct order for the program to read, and then we can go ahead and start this. So we're going to open this Clark-Y data. Click exit on that. No data has been done yet because there's no data analysis. Go to direct foil design, and you'll be able to see that this bigger airfoil around this symmetric one is the cambered Clark-Y airfoil, which again is listed down here. Next, we need to do some analysis on this for the project specifically. So we need to go to, where is it at? Direct analysis. We then need to go to analysis, define analysis, type 1. We're going to make sure our Reynolds number is 1 million for the project, and click OK. Now this is a sequence from -5 to 20 with a change in angle of 1 degree, and we're going to click Analyze. Exit. So here you can see, let me zoom out of this a little bit. You can see that all the graphs are being displayed that are necessary for this project. You have your lift coefficient versus alpha. You have your lift coefficient, actually, no, wrong one. Lift to drag coefficient ratio to alpha, and you also have your lift versus drag coefficient. This graph, and this graph are the only ones that are needed for this report. In order to get the data for these specific graphs, all you have to do is right-click like this, go down to Current Graph, then go to Export Graph. When you click the Export Graph, it'll prompt you to save this set of data points into a file, a .csv file, which can be opened in Excel. Again, I already have this completed, so I'm going to click Exit. I'm going to minimize here, and I'm going to show you what I currently have for that. So I'm going to go to XFLR5, Project 1, Clark-Y, and we need the CL versus alpha graph. Just like this. And again, your data points will come up just like this. This I added. This was like a maximum value that I came up with for later in the project. But this is the lift coefficient here. It's just, it was named something differently. But in order to get your lift curve slope, all you have to do is just plot this onto a simple chart. So I can show you how to do that really quick. We're just going to go to scatter chart. I'm going to go to select data, add this Clark Y. Our X values are going to be our alpha. And we're only, actually, I'll show you the entire graph first, and then I'll edit it a little bit. So this is just showing you that these graphs can be correlated. Yep, so that's the graph you will see from your XFLR5. Same exact shape, same exact numbers. And the thing with this is we can actually calculate the lift curve slope by cutting off our data points at 10 degrees, and that'll give us an easier trend line. So what I'm actually going to do now is reverse our X values a little bit and change them up. So now we're going to go from alpha from -5 to 10, like so. And then I don't think I have to change these, but I'm going to because OCD. Bring this down to 10, just like that. Okay, so now we have our lift curve line, but we need to get the trend line in order to get our slope. So we can go down to trend line, click here, click more options, and then here we'll be able to actually get our equation. So we just click this little checkbox, and it pops up here. Now, if we take a look at this number here, I'm just going to show you, we have our slope of 0.1034, and we're going to go to my assignment really quick. I'm just going to show you that this slope is the same as, you know, what we're calculating from what I got from XFLR5. So you're going to want to do this with every other airfoil. When you take this data, you just want to use this trend line and get the lift curve slope, and it's the same process I just did with this one. So let me exit out of that. I'll save my changes. Beautiful. All right, so next, let's see here. In order to find the, actually I probably should have kept that Excel file open. In order to find the min, or your maximum lift coefficient, all you have to do is just highlight, or actually no, you don't even have to do that. You can just click equals max, M-A-X, parentheses, highlight all your data, and close parentheses, and it'll give you your maximum value, which this one is located at right here, which is at 15 degrees. So again, that's where all this data comes from. You can just compare all your data points in each of these individual files. Okay, so we'll minimize that. Now we have to look at changing our aspect ratio, because our aspect ratio is constant, our taper ratio is constant, but we need to get to what the assignment asks, which is a taper ratio of 4, 8, and 12, and a taper ratio of 1 exactly. So in order to do that, I'm just going to completely exit out of that project and restart it up again. Start from scratch. XFLR5. I already have the data in here. But again, I don't want to show you the data I've done. I want to show you the process it took me to get to there. So actually, I think I go here and, yep, right here. Perfect. So again, like before, we have to load up the Clark Y airfoil. So we're going to go to Open, Clark Y, exit, Analysis, define analysis. Make sure we do this as 1 million. Okay. And then analysis, define analysis. Okay, now it should allow me to go to File, Direct Analysis. There we go, Analyze. Okay, so this is where we were before. Now what we're going to do is we're going to actually go to File, or actually no, Analysis. We have to do a batch analysis. And the batch analysis is basically going to allow us to account for the different Reynolds numbers that are going to be on the wingspan. So from here, I did 500,000 to 4.5 million with an increment of 20,000. This is going to take a while to converge, but it's necessary to get accurate numbers. So as you can see here, we're going to get our graphs elongating in a bunch of different directions, and that's just you know, every increment that you see on the screen here at 20,000, it's going to go and do a completely new line for each of those increments between the bounds 500,000 and 4.5 million. So it does take a little bit to do, but again, if you decrease your increments and you increase your bounds, you'll have a better result, and you won't have an issue with convergence. Now, I believe there are some slight issues with convergence, but nothing that affects the overall report, so it's not really worth mentioning. But again, if you're having issues with convergence, I would suggest just changing your bounds and changing your increments, and you know, waiting a little bit longer is sometimes worth it in order to get your results more accurate. So this is taking a little bit longer than expected. It should take about another 30 seconds from what I'm looking at right now. So we'll let that kind of run and do its thing. And just letting you know, batch analysis is necessary, because if you have a Reynolds number that occurs on the wing that is not in this range, you will not get the results you need for the report. We're getting there little by little. Our graphs just keep getting bigger and bigger and bigger. And again, though, that's what we need to see, because again, we need to take into account to the possible Reynolds numbers we could account when we do our tests on the wing, which we will do next once this finishes its iterations. Seeing some numbers pop up there, getting very close. It's probably the longest part of this entire project is just waiting for your batch analysis to finish. Should be done in like 3, 2, 1, and done. Beautiful. Now, as you can see, some points are unconverged. So that means that like out of all these different graphs, there's a couple points that didn't completely converge, which again is okay for this graph. So I'm gonna click exit on that. Let me get zoom out of the way here. I can't get zoom out of the way. Okay, click exit. So then we're gonna go to File and Wing and Plane Design. So I'm gonna go to here, then go to Plane, and we're going to define a new plane. We're just going to leave it as plane name because this is a demonstration. We do not need the elevator or the fin or the body or the biplane. We just need the wing. So now we're going to define our wing and the way it looks. So right now what you're seeing here is the original Clark Y airfoil with a taper ratio of 1.64 and aspect ratio of 13.79. So in order to get our aspect ratio, we're on a rectangular wing. We want to essentially adjust our chord length and our wingspan. So what you're seeing here, these numbers here on the Y, is actually going to be half of the wingspan. So if you want to create an aspect ratio of 4, which would be equal to, for a rectangular wing, it would be equal to B over C, B being the wingspan and C being the chord length. We want to make this to 8. And we want to make each of these chord lengths to a rectangular width. So our aspect ratio would end up being 4, which is exactly what we're looking for. So let me try to zoom out really quick on this. Beautiful. We want to make sure we're calculating from the Clark Y airfoil like this. And you can see we have that 3-dimensional shape now, which is beautiful. So we'll save that. We'll save that. And here is our plane. So now we need to get our analysis. And again, all these steps right now that I'm doing for this specific airfoil, you can do with the same thing with the aspect ratio of 8 and the aspect ratio of 12. Talking about what I did personally, I used, for the aspect ratio of 4, I did a span of 16 meters and a chord length of 4 meters. For the aspect ratio of 8, I did, what was it? I believe it was it 9? No. I'll have to show you the results afterwards, but essentially you're just adjusting your span and your chord length in order to get the aspect ratio of the desired amount. So anyways, let's get to the analysis portion. So we're going to define an analysis. We're going to do 10 meters per second. And as you can see here, our batch analysis actually accounted for these numbers because we did between 500,000 and 4.5 million. So this is included in it. So we should be okay. So we're going to click save. And then we're going to go to sequence because we're sequencing from -5 to 30. It should be actually 20. And 1 degree increments. So we're going to analyze that. And as you can see, we get this induced drag little thing behind here. We get the viscous drag. And we're going to actually animate this just so you can see as the angle of attack changes, your values change pretty significantly. I'm actually going to stop the animation on, oh, that was not on 7. You can stop the animation specifically on 7 degrees, which is what's required for the project. So I'm going to actually wait till that goes back down for a second. Let's stop it on, I want to stop it there for a second because I got this little email pop up. Beautiful. So we stopped it at 7 degrees exactly, which is what we need. So in order to get the data for this 7-degree inclination, we can actually go to here. And we can see our graphs total for, our increments from -5 to 20. If you want to see a specific angle of attack in regards to like the data at that specific point, we can just go to this little graph here, and you can define what exactly you want to see on the graph. So for right now, we have the induced angle. If we wanted to get like any other parameter, we would just go to current graph, define graph settings, and then induced drag coefficient is another one we have to do for this project, so I'll do that. And as you can see, your values here are below. So like alpha is 7 degrees, tells you your lift coefficient, your drag coefficient, all that good stuff. And over here, it tells you your geometric dimensions and stuff. So in order to get your overall data, just like before with the Clark Y airfoil, you just want to right click on the graph you want. You click current graph and click export graph. And again, you can bring all these values into one Excel file and make things a lot easier, which I will show you momentarily. But again, same thing with this one. This is going to be your induced drag graph. which is shown on here. I'll show you my induced drag graphs. So this is actually specifically for this one, the Clark-Y aspect ratio of 4, span versus induced drag. It's the same shape we're seeing right here. So that's, again, that's representative. Let me quickly show you the Excel files that I have showing all the different data that I've collected over this project. I'm going to go to XFLR5, project 1 Aero, and we're going to we'll just do alpha versus CL. So as you can see here, this is all the data that I've collected from these graphs. Let me just show you again, the graphs from right here. For each of the wings, I've collected all of these graphs and combined them onto this Excel sheet. And from there, I was able to actually combine all these different graphs together and give us an overall look at the different, how your lift coefficient changes with different aspect ratios and things like that. And that's just for lift versus alpha. Let me show you the other files really quick. This is CL versus CD, completed with the graph. Minimize that, and we're going to show you the CL, CD versus alpha, just like this. Well, I'll talk about this more in the results, but this is very skewed due to the taper ratio. These all have taper ratios of 1, and this has a taper ratio of like 1.69, so, or 0.69, something like that. So it's a little skewed, but nothing. It still is useful for results. Exit out of this. Don't save. And then these two, the span versus induced drag. Oh, so that opens up. That's just going to be the individual plots for induced drag across the different planes or wingspans. Let me exit out of that. Save. And the last one is wingspan versus induced angle, which, as you can see here, wait till that comes up. Yeah, all the graphs are representative of what we see in XFLR5. So exit out of that again. Exit out of that. Don't save. Minimize. And then I'm just going to quickly look at the project again to make sure I'm covering everything in this report. Maximum lift coefficient, I already went over how to do that. In order to do that, you just go into Word again, and you can just highlight a column, or you can just do the equal sign, do equals max, and then highlight a column, close bracket, and it gives you the maximum value, and then you can just find the corresponding angle of attack. Now for the calculated induced angle and drag, this is the last thing I'll probably cover, because again, everything else is kind of self-explanatory. You just use Excel and do your values to calculate it. Everything else in XFL was pretty much done already. You just have to apply those to different airfoils and different aspect ratios. So for the calculated induced angle and drag, you want to use an equation specifically for that. So in order to calculate your induced angle, it's going to be CL squared over the pi times your elliptical distribution times your aspect ratio. If you have an elliptical distribution of 1, you don't really have to worry about the E too much because it would just be 1 and it wouldn't cost too much. But because we have different elliptical distributions and we can actually find those from the graphs that were posted on the PowerPoint in class, we're going to have a bunch of different values for those different induced angles and drags. And after doing that, essentially this is what I get for each of the angles. They all have taper ratios of 1. The Clark-Y standard airfoil has a larger aspect ratio of about 13.79, I believe, which is considerably larger than some of the other ones, but it does have a taper ratio of greater than 1.0, so it was not included in here for analysis. So overall, I'm pretty sure that concludes this assignment. I don't believe there was any other. I can actually double check one more time to make sure I covered everything. I covered the airfoils, I covered the taper ratios, covered all these things. 7 degrees of attack, I told you how to do that. At 7 degrees of attack, you can calculate your induced drag and stuff. And yeah, so I've covered everything. Again, I've done all this ahead of time because this overall project does take a little bit longer just because, it's a tedious process. Very simple and straightforward, but given, everything we had to do, it took a little bit longer. So again, made this video ahead of time. in order to, or I did the results ahead of time, so I had also a better explanation of things in the video. So thank you so much for watching, and yeah, I'll see you next semester when I'm taking Design of Aerospace Experiments. Thank you so much.